Recording now. Yeah.
And we are going to continue that part of continual learning. So let's make a brief recap
Well,
on what we have.
you are not sharing the. Yeah. Thank you.
Start with our recap. So the problem of continual learning is dealing with historical program. So when you have a sequence of tasks or a sequence of data sets, you want to learn through your environment, through your literature. The problem usually is that you have a sort of behavior called historical program. So when you start learning new capabilities, new skills on the new classes or on the new classes, the model starts to forget the previous classes or the previous knowledge. Okay? And we have discussed that this is basically due to the optimization algorithm, whereas is Greek installed philosophy. So what does it mean? It means that when we start from an initialization and learn cascade, we go toward its meaning, its meaning white space. That if you have another task B and not and stop optimizing on data from task A, we end up in a meaning for task B. But there is nothing that guarantee that the new optimum is still a good point for testing. So you continually go objective is to find a good point for both tasks. Okay, so that's sort of intersection between good performance in task A and good performance. But the problem is reaching that point without relying on data from this. So this is just a very recap on all the concepts that we have already seen. And we discussed first approach we discussed for the continual learning is called elastic wave constraint, EWS. The idea behind that you see is that we can mitigate catastrophic forgetting through the concept of regularization. It means that when we are on class B, when we are optimizing on class B, we do not only optimize the corresponding function, but optimize another, also an addition, an auxiliary loss function that in particular gives a penalty on the displacement we are doing. We are doing in weight state. So this is the optimum for the previous task as A. Basically, we do not want to move too much from that. And in particular, we weigh the directions, some that are really important for the scale. So if these weights, let's consider a particular weight from the estimation here. If this weight is really, really important, so its E is really high, then we are basically asking the model to remain close to the original weight. Okay. So basically, PwC, the idea is to enforce regularization and remain close to the previous weight. And the important score that computer tool measure it's called Fisher information matrix that basically encapsulates and embodies the geometry of the loss landscape around the. Okay, so if the importance is low, if the region around the meaning is flat, no? Then corresponding feature value is low. What does it mean? It means that we can change value of that way and the loss function will not. Otherwise, the mean is sharp, then the corresponding feature information matrix that way will be high. So it means that we cannot change too much. Okay? We should be close to its value. So now let's go to see other concepts related to continual learning. Not only purchase but also protocols, evaluation and experimental protocols. No? And these are some datasets you will find in literature. And one, the most common choice is basically dividing your datasets into tasks, where each task contains disjoint set of classes. Okay, so I can take plus one and for analyst and ask in plus one the network to classify zeros and ones images. Then you go to plus two and classify two and three and so on. And there are other also other kind of protocols, no? Or benchmarks. For instance, in rotated list, you want to basically the digits, the classes remain the same. What you do is in subsequent tasks is to change the rotation of each unit. So this is basically simulating a scenario in which the set of classes remain the same, but what changed is the domain, is the input. So there is a sort of distribution on the input domain, and we want our model to be learn how to classify images with varying rotation. And in each task we show a different. These are kind of protocol that is different from the first two ones we could see. It's basically on the idea splitting based on this. Another benchmark or idea to simulate learning from a sequential data. Another idea is based on permutation. For instance, is in this case, it's very difficult because in each task, the set of classes remain the same. What I do is just apply a different permutation. So in task one, I apply given permutation, with a second task, I apply another permutation on digits, and in each task, basically, what people do is apply the same permutation components. Okay? So just to let you know that there are a lot of possible approaches to simulate sequential data or basically straightforward changing tasks. Okay? The most common one is splitting of classes, but even requires based on shifting the input. Any questions? So basically, as you know, I would say machine learning or deep learning application, they are after a training phase and test. Okay? During training, we expose the model to consequences of that, and during that, we want to evaluate the model for no tasks. Okay? So starting from level one, first one, and basically you want the model to perform well. Okay. Usually, as you can perform multiple efforts on each task or multiple training efforts, and it's often called offline continual learning. In offline continual learning, you are allowed to revisit the task or the task certain task. You are allowed to revisit it for multiple times, for multiple efforts. This is called offline. Instead, there is another scenario that is called online functional learning, where you usually allow the model to see data at once, just for one. Okay, you can find research on these two kinds of protocols. Why? You have a feature or research in favor of offline or online learning. You feel it's better to test approaches in the online learning, so just one example. So each example is seen only once and is trained only once. Or instead, where in the offline scenario where we allow multiple class investigators. What do you think?
Offline is easier.
Yeah,
Yeah,
yeah.
you can repeat the data
We in the offline.
in the online, but in the online, you may not fit sufficient video.
Exactly. So in the online scenario, basically the offline scenario is easier. Okay, so we are allowed to pass and we are basically allowed to learn the things. Okay. Instead, in the online scenario, we have this difficulty of seeing example only once. And the problem with online critical learning is that usually we have two risks. The first one is custom forgetting, and the second one is underfitting. We are entangling underfitting and custom forgetting. Why? Because we do not have much time to learn the dust. So we cannot say that after that dust, the model is good on that dust. This instead is not true in offline functional learning, where you have to guarantee that after the end of that task, the model has learned correctly that task. So the problem with online functional learning is that usually it's quite hard, difficult to assess whether the model has better performances due to the forgetting or due to the underfitting issue. Okay. And sometimes there are approaches that perform well on continual learning on online learning just because they can learn quickly the data. But learning quickly the data is not basically avoiding forgetting. There are two different things. So for this reason is maybe offline personal learning is easier, but it allows you to focus on the actual challenges of computer learning that is avoid and not avoid or other. Okay. So hyperparameter tuning and cross validation is also difficult. So there are some protocols based on splitting the training set, but nothing established. So you can find some papers that propose some ways to perform hyperparameter tuning and validation based on basically taking the current data set, and splitting it into 20 orders. And about the metrics, how we measure and performance. Basically, with the others, no? If we deal with the classification, we can get the average accuracy on each task. So we take the accuracy on the first task, the accuracy on the second, and average them those together. This is computed after the end of the last task. And also we can check the average accuracy at the end of each task. Okay, so even at intermediate points during the learning process. And the accuracy is the good. Is probably the best metric if we consider balance specification and so on. And but there are also other metrics we will consider For instance, the backward and forward transfer, you can find their definition in this paper. In the backward transfer and forward transfer, we are usually interested in isolating forgetting. So the idea is trying to measure how much the model has lost in terms of accuracy with respect to each task. So this is the backward, and this is the backward transfer. So, and the forward transfer is that a measure that measure how much we are gaining on future tasks, how much we are transferring, how much knowledge we can transfer to future tasks. So, in general, the average accuracy is often called also final average accuracy because it means that we are computing that measure at the end of the task. So the final average accuracy is the clearest method you can find and you have to measure to assess models, but there are also other methods that try to check forget. So forget is just the displacement, the differential in terms of performance. How much I lost, how much accuracy I lost for task one after I learned on last step. It's incredible. So basically, what you when you see a paper on continual learning, you will end up with something like plot like that. What is this plot? This plot is basically for each task here, it measures the average accuracy on all tasks before and including that one. So, for instance, when I am here at task 6, I am measuring for different methods, for different approaches, the corresponding average accuracy on all tasks until 6. All of them. Okay? And you can see that this kind of plot usually a decreasing trend. So it means that the model is experiencing a sort of forgetting, basically. And the more the tasks we have, the more forgetting usually we have, because the more knowledge we are asking the model to learn. And what we want to do is being the guy. Okay, is always be on the top part of the region. And why this plot is important? Why? I could say that it is enough to have this number, just this number at the end of the list. So I could say that it is enough. What do you see in this plot as points formative? If you see this, you forget you're not. I mean, but you're at the top. It's like you're not forgetting from the tasks. We can see the trend basically. We can see what happens in between task 1 and task 2. We can see all the history. So we have a complete overview of what happens. So while the final accuracy is just a snapshot of the final after the final task or the last task, instead through this plot we can see, for instance, if there are some changes in the behavior of the approach, some up and down. What usually when we work on a new method approach, we monitor this up and down in order to discover problems or to assess the approach in general. So this block are usually very informative, even to demonstrate someone, for instance, the reviewer, that it's not just about the final task. Our model is good on not bring all tasks. Okay, so the model is consistently narrowing point in time. Okay, so this is about metrics, accuracy, and final accuracy for the trends for and it's basically, as I said before, difference in terms of performance. But these that are three main evaluation scenarios. Okay, and basically every protocol, every benchmark on continual learning can be classified in one of these three classes. Okay. In task incremental learning, basically, we still divide the classes into tasks. So class 0 plus 1 for plus 1, class 2 plus 3 for plus 2. Okay. But in incremental learning, usually at different times, we are given with important information. No? That is, at different time, we know the task identified. So we know, for example, we want to classify, we know the corresponding tasks. The example comes from. Okay. So we at different time, basically we know X, so the image, and we know its corresponding task. Okay. This is called task incremental learning. In class incremental learning, so that is the second section we see. In class incremental learning, the approach basically to split the data, that the approach remains the same. So we split classes in these joint sets. But what we do is to avoid giving the model the task name. So the model at different time in class incremental learning does not know the task, the example from. Okay. Now, what do you think about class incremental learning and class incremental? Which is the easiest one and why?
Easiest one, I think, will be task incremental learning.
Yeah.
Since you have in first time the task number, you will have more information about the task that you're trying to do. Meanwhile, in class incremental learning, since you don't have the task, you have less information.
So, for instance, how would you explore the class identifier?
Usually it was deployed, maybe you can add it as a parameter in the network in order to compute the embedded.
Yes.
So you say, okay, I want the embeddings of the 0 and the 2 be the same, maybe, and the 1 and the 3 be the same. And now I have a task identifier, I know which class should it release.
Okay. So basically, if you add task identifiers, you put one subset, for instance, of parameters devoted to task one subset of parameters devoted to task 2, and you can switch even the task identifier. You can switch between task 1 or either task 2 to read okay? Yes. Or even if you do not have this thing, even if you do not have specific parameters, and let's try to consider what happens at the final layer. No? Final layer, we have usually the classifications. Classification heads are basically final projection that starting from the hidden application plus the prediction for each class, the class wise. So if I have the class identifier, for instance, let's suppose that my example is from class 1. What can I do is I can mask for these probabilities. I can set to 0 these probabilities and leave just this one. So when we have the task identifier, we can basically select the corresponding classification accordingly. No? So we know that all the classes, all the potential classes are here. So I can just mask out these classes from the okay. So in this case, I am avoiding possible interference between class 2 and class 1. The only interference I am dealing with are in between class 1, in between classes of class 1. Okay. So class incremental learning is the hardest scenario for this because we cannot rely on class identifiers, and we could have possible interference issues between the prediction of class 2 and the prediction of class 1. For instance, for this image, I could say that the corresponding class is the 2 or the 3. This is avoidable by designing the task incremental learners where we have the task identifier. Any concerns or oh. Okay. Can I in class incremental, do you know is a good idea to guess that one? To predict that one? To predict the task identifier? I will say, okay, I do not have the task ID, but what can I do is trying to predict the task ID with the method, for instance.
Okay. But that would be the same problem, right? We have a class in technical learning because you don't know how many tasks you have. And in order to classify this task, you need to identify, okay, this sample belongs to this subset of class. So we get the same problem but simpler.
Yeah, exactly. Because usually it will be, we would still have a strong forgetting, but on the task level. No. So because we have to learn a neural network that maps images to task identifiers, but this network will suffer from that structure again. So it's a chicken egg. It could be a chicken egg problem. However, the actual which is still try to guess the tasks, okay, or maybe a proxy of the task. So a sort of mid-level representation between classes and classes. The third one, the last scenario we see is called domain incremental. Okay. And I don't know, is that this part? Okay. Okay, please don't consider this image because it's outdated, so it's probably. But basically, in domain incremental learning, it's maybe it's better we see that in domain incremental learning, usually, no, for we can consider the first row here as class 1, the second row as class 2, and class 3, and class. And so in domain incremental learning, the set of classes remains the same. So in class 1, we classify 0, 1, 2, 3, 4. What we change in this subsequent class is the relation or something related to the name. So what we do is to simulate a shift on the images. So domain while we said class incremental learning do not apply any kind of explanation to me because the split is based on the classes. Instead, in domain incremental learning, what we do is maintain the same set of classes, no, for each task. So 0, 1, 0, 1 in this case. So we have one classification tab with all classes, but what we do is change the representation for the integer. So for instance, let's suppose here there is a zero but rotated with a different rotation angle. Okay. We are with this protocol, we are simulating what happens when the classes remain the same, but there is something, there is a shift in terms of distribution. No? Do you have in mind any realistic scenario where plus incremental to incremental could be applied or could simulate?
Trzeba to data change photos of animals and you don't shift to the sketches with the same animals.
Exactly. So for example,
Problems.
or for instance, the same animals, same species, but in different habitats. Even so, habitats A here or country A, and the same animals but in a different country or a different habitat. It could be out of the system. So we are dealing in we want to learn the same representation for that animal, but the animal is seen in a different environment with respect to that. This is a good explanation of continual learning, no? Or other ideas?
In internal learning, happens a lot. For example, that there is people who, for example, pictures of a phone. If we live in different countries, we have or even different cameras, have different settings, different exposure, and all these things contribute to our learning shift. So
Yeah, even in that case, it will be, we can fit it in Romanian context. So, in, let's suppose we use different instances. Let's suppose it is the general case where the target is the same, but what we do is apply changes in the sensors. So we use different sensors, shifting, for instance, from RGB to infrared sensors, or making some changes as you mentioned, for just images of different configurations camera with. So, and yeah, this is another example. Others.
Finish with lights and then it's different. It's very
So, for instance, this is the case of video surveillance applications, in which we have a sort of shift, no? Or a sort of transition between daytime and night. So it's another example that still you want to test objects or multiple object tracking and whatever. So it's another. Do you have any idea that related to the class incremental learning where it is reasonable to assume different classes?
a typical problem would be like, for example, Google Photos. So Google Photos, they classify the people that appears in the picture. So you can always introduce new people, and then they have to detect this as a new person, and the next photos be able to classify that person as a new person.
Yeah. For instance, dealing with new identities, dealing with new identities or new concepts, no? Because in domain incremental learning, yeah, the concept remains the same. So it remains fixed from the beginning to the end of the learners. Instead, in class incremental learning, even that, what we do is introducing new concepts, new high level concepts. And we want the model to retain all high level concepts. Okay. Okay. And there is one scenario called one general continual learning, but that probably is the most difficult one, and even from the most realistic ones, in it, we try to go to both, no? So what we do is, in general, is to have a sort of hybrid approach where we have both class incremental learning, so we are using new classes, and also domain incremental within each task. So basically, these digits are shift the distribution slowly shifts during training, and at certain points there is a sort of sudden distribution shift given by changes in the axis. Okay, so in general functional learning, it's called generalization of both domain functional learning and custom functional learning, where we basically simulate both phenomena. Okay, so the input distribution is slowly and smoothly shifting, and the class distribution, class distribution is suddenly shifting. Okay, and the model has to manage both. Okay, has to be robust against both kind of shift, the smooth one and the sudden. Okay, there are also other flavors of functional learning. For instance, there is federated functional learning. Federated functional learning your clients distributed, and each client is subject to a sort of objective because learns from sequence of tasks. This is the, for instance, catastrophic federated continuum learning. So where we mix the two domains, federated and machine learning, and also you can relate to a lot of possible problems and tasks. For instance, noisy continual learning. So learning from a set of noisy annotated examples. So the idea is that, for instance, one very expensive thing here is we are supposing to learn this data not from a string of tasks from a string of data that may come through sensor or voice in general. No? And when you are learning, we usually supposed to have the ground truth. Is this reasonable? According to you, to have examples annotated perfectly online? Why? If no.
People get paid for this and they just want to make money.
Yeah. So one problem is that and then we, in order to have why here we have to pay people, we have to pay the annotation, and if we can avoid annotation, okay. So for this reason, you could find a lot of literature about unsupervised continual learning. So trying to learn that kind of concept without relying on what. Or semi-supervised continual learning. Semi-supervised continual learning is supposed to be generally assume that we have only a few examples annotated here for each task. For instance, we have 95% of example without annotation, and we have 5% of examples that are annotated. So this is the same supervised one. But there is another reason behind management that should allow you to avoid relying on annotation or considering annotation something somewhat noisy.
There are microphores sensor cells, but doesn't
Exactly. So the idea is that if you want to learn something online, then you do not have much time to correct errors. we do not have much time to fix errors or to annotate the errors. Let's consider the case of semantic segmentation. Semantic segmentation, when we annotate data, there is someone that on the computer each pixel. There are a lot of automated tools that split this process, allow you to split this process, but still remains a slow and very intensive, time intensive process. So in continuous learning, if we want to use the labels, the supervision, we should assume in a practical scenario that this Y is variables, because it doesn't annotated by users that upload the data in Rush, or for instance, this Y depends on prediction of other models, or the Y depends on noise measurements of sensor or anything. So it makes sense to work in a scenario called noisy continual learning. So continual learning, where we assume that we should not trust entirely the Y, the ground truth during training. And this, for instance, is another example of settings people find identification. So continual learning in a setting in which I cannot trust entirely the label is attached to the system. Why? If we want to learn online, probably we not have much time for errors or to annotate, and neither much money. Okay. The last pointer to existing protocol, but this discussion about protocols and benchmark is, I feel that it is important because there is no there is no one good or perfect continual stuff. Okay, but it really depends on your application. It really depends on your final application. So we want basically we want to we should find the protocol that fits the most our final task, our final industrial application, and so on. So, and for instance, in that incremental learning, what these are some minor examples, but still are important and valuable. And in that incremental learning, for instance, the set of the classes remains the same, no transformation is applied, we just see in data. So new acquisitions, for instance. So the classes remain the same, no shift in terms of distribution, just we observe new data. It's like we increasing the data set, the size of the data set during time. And we want the model to still be efficiently from that data set that grows over time. Okay, so this and the discussion about the protocols. So how we evaluate our models, our continual learning models, and how we assess the performance. Now we are going to see some approaches, some methods, okay, on continual learning. There are basically three kinds of families, okay, from very high level. There are three kinds of approaches. The first one is called architectural methods. In architectural methods, basically we are expanding the architecture, we are for instance, we add some layers, some parameters to accommodate the knowledge. There are, we said, regularization methods. We have already seen one approach to that for regularization. That is last. In regularization method, what we do is to penalize to the loss function, penalize deviation in important ways. Okay. Or more in general, we devise optimization objectives in the loss function. We devise auxiliary objectives that prevent the from change. So this could be based on weight importance, but we will see that we could use knowledge distillation, for instance. For instance, for transferring knowledge from a previous network, from the laptop we observed previous task, what to transfer in e-sport and knowledge to the current. Okay, this is another approach to this. And another approach is that based on the concept of reaction, replay. In reaction, what we do basically is retain a subset of example from past, no? And so we maintain a sort of memory, so it is called memory buffer. So a sort of shared in this space where we put examples from past tasks, only for instance, the 10% of past data. And during training, we sample a batch, training a batch of examples from both the current task and both the memory buffer, and optimize them. So the idea is take in replay videos. This is called replay because basically what we do is we continuously train on that examples. We reference that examples. We continue to train on examples from past tasks, and these examples are stored in the memory in a sort of buffer called memory buffer. This buffer has a fixed capacity, and we try always to optimize always on both data. So data from the current task and data from this kind of. Okay. Yes.
How do you select the instances of the products? And randomly on the best candidate or whatever synthesis can.
The faster one, simpler one, the many styles of the one is probably yeah. So manipulations. So I think I even at the end of each task, I take the 10% of images in that's a reference. And there are other approaches that instead try to compute the importance of each example. So the idea is to store only the examples that are really important for the piece. So the idea is trying to extract all these examples in which if I train on this example, then I have still a good knowledge of all the results. Yeah, the problem with these approaches is usually that this requires time, and yeah, basically we will see first possible solution. However, so basically in this case we expand the architecture. In this case we avoid changes. We try to transfer knowledge or avoid or prevent the model from changing. And in this case, so if we were playing instead, we maintain sort of memory. So a subset of past data, and each training iteration on the current task, we sample from both the current tasks of the current task, and we concatenate the corresponding example and give it to the model. Okay. Any illustrations about that? About replay method for the arguments.
So as you said, you remember the previous classes and sometimes in buffer. And the model is just the retrain again and have on the same region. And we
Yes. One problem of replay method is basically repeating what we observed in the past with this kind of approaches. Is basically that the loss function, the loss value on buffer data points is basically zero. Because this example has been we have trained the model on this example much time. We have spent much time to memorize to train this example. The problem is that being subject to overfitting is not so problematic as being subject to forgetting. So it's better to overfit this example than forget that. Because if we overfit on this example, we still maintain a capability on the corresponding task. Even if that these capabilities are we reduce that capabilities due to overfitting. Okay. But if we do not train, we just import in overfit. It is much more severe than overfit. This is basically the issue. So it's something that we accept overfitting. We could also provide a lot of approaches to mitigate that behavior, but usually in rehearsal approaches, we accept overfitting of data points in order to prevent even more useful communities Other question?
Knowledge distillation could be seen also as an architectural method, no? Because you have a copy of a smaller method. It's like a different architecture or
The difference here is that in architectural method, what I am basically extending the model and that is used for doing inference. So I'm taking the model that makes understanding its set of parameters. So the new parts that I add here are in the backbone I use for it. Instead, in order to I would say it's a separate model, but it is useful only during training to guide the model. So in the memorization method, basically we act on the loss function on the to provide additional. Please note that this family can be mixed. We call that replay method that have also representation. For instance, in our one of our paper, fast, we mix replay with regularization exactly to avoid overfitting on buffer data points. So we retain a subset of past examples, but devise an additional regularization loss that prevents that prevents overfitting on buffer data. Okay. Or for instance, you could let me see. Yeah, some works architectural methods are mixed with the regulation. But is most frequent one I've seen is mixing the replay approaches and regularization. Okay. So level of traffic forgetting. We are looking for basically because we are imposing the weight sharing. No, each task basically every task relies on the same set of parameters, on the same method. So task B, while we learn on task B, we basically modify the same set of weights we have learned for task A. For task G, we basically modify the same set of weights we have learned for task C. Okay. This is the problem behind program. We are imposing weights. So each task shares the same set of parameters. Okay, so one approach to avoid that is basically based on architectural. The idea of architectural method basically is that of devoting different parameters for different tasks. Okay, very easy. So when I have to learn a new task, I instantiate a new subnetwork, for instance. Now we could have some solutions that apply these approaches, general approaches, only on a portion of the model. For instance, the first layers are handled with this structure, and the last one are studying compound with that. It really depends on the task we are considering. But the overall idea is that when we have a new task, we add new parameters that are tailored for that task, that are developed for that task. This is called, for instance, progressive neural networks. In progressive neural networks, we progressively increase the complexity of the problems.
You need to know when a new task appears.
Yes, you need task identifiers. Even at interest time, at any time, I need to know the end of one task and the beginning of the other in order to increase the model size. So basically, I need task identifiers. So I need to know that this example is from +2 and or +3. First problem. Second problem, I need task identifiers even at inference time. At inference time, I have to know which branch activate. If my example is from +2, then I should activate this one. If my example is from +3, I should activate that. Okay. So, for instance, with these kind of approaches, I cannot perform class incremental learning. Okay. Or I should find another way to guess task identifier. So these approaches are this kind of other techniques you see.
It is getting bigger in size. I mean, we have a big model, then this is not scalable.
Exactly. So for each new task, I have to add a new set of parameters. Okay. And this is not efficient. Okay. Do you have any solution to mitigate that?
Maybe doing something like a mixture of experts.
Mhm.
Like in neural networks, you have a model that is involved in a well, and then you just try to make sure that at one time the gating function distributes according to the task in different experts.
Yes. Yeah. So the idea is based on based on having sort of mixture expert at each layer that selects the input. That selects which part to activate based on the activation. Yeah, it could be a good idea. But if I suppose I want to add in a straightforward manner, I want to add just inside of it. Do we have in mind any solution to mitigate the increase in terms of memory complexity of given by introducing a new set of parameters?
Using a lot of the
All the things that we have seen yesterday. So all the approaches we have seen yesterday give us a lot of methods and approaches to reduce the number of parameters we should use to increase the size of the weights. For instance, I could have a solution where I add a LoRa. So given when I have to learn on a new task, I can instantiate a new set of LoRa, and then I can learn LoRa. Okay. So you can take all the techniques we have seen yesterday, and you can apply to continual learning in architectural approach. Yes.
There are any assumptions over how similar the tasks are? Because, for example, groundworks, when you have a model that is good at generalizing, maybe, for example, a convolutional network trained on images,
Okay.
and then the updates are seen to be low run, so without the composition, but if tasks are to way more different, then the rest are going to perform well. So there are any assumptions.
Usually, the assumption you find in that kind of usually the assumption is that this preferring it means that the first task you do not start from scratch. You start from a model that has been prepared on image, for instance. That is very I think that this is very realistic because in real world, basically when you start learning start from something that has been already prepared. So in many recent works about continual learning, you are allowed to start from the first class, you are allowed to start from a preparatory. So in this case, you would apply LoRa, basically because you start from a really good model and you are finished with the approximately will be LoRa. Okay. So this covers the part of architecture. But in general, if we start parameter different fine tuning, we still have the problem of increasing the size. So, and we are progressing. For instance, there is something. It's not only based on the idea of expanding the network, to be more precise. It's not based just on the idea of expanding the network with a link column. This is called column. But also the idea is to enable a sort of transfer between branches, between columns. In progressive neural network that was the former approach proposed for architectural domain. In the idea is to have between these layers, the idea is to have sort of lateral connections that allows you to transfer knowledge from the model learned on the first task to the model learned on the second one. Okay, so you could have silos, vertical silos that are independent, but also you could have some sort of lateral residual connection that allows you to transfer knowledge from the network learned from task one to the network learned from task two. Okay, so not really vertical silos, independent models, but models that can communicate and that can exchange knowledge, basically. Okay, this is the idea of progressive neural network. So, and expanding the network with new parameters, but these new parameters can receive information from past parameters. So, because one very really interesting area is that we can reuse knowledge. We can reuse all computation here in order to maybe make training here faster. Okay, because we are basically taking advantage of something that has been already there. Okay, about the disadvantage, I I feel that we have already discussed it. So the problem is about knowing task identifiers in order to select, in order to make routing. Routing is that kind of problem. General network when we have maybe different parts, and we have to group the information in different segments of the model. So in this case, routing, the problem of routing is the problem of finding the column of given that we should use for our example. Okay, this kind of just identifier. But with mixture of expert, we can put various mechanisms from scratch. Okay? Yes. So using our requirements, and also there is bound on the number of tasks that bound basically our this memory is the size of our memory in each tool. Oh. There are some other approaches. For instance, I are the attention to the task. Here, are the attention to the task is based on the idea of mixture of experts. So basically, try to learn the task identifier and using something similar to mixture of expert layer. But I'm going to talk about Puppet because it's really interesting. In Puppet, basically, what we do is to try to avoid using new parameters. In Puppet, what we do is try to enable which how. Let's suppose I start from class 1. Okay. You know that with neural network, I can after training, I can apply pruning. How many of you know the concept of pruning weights? Yes. Okay. So what can I do here? After training on class 1, I can prune, for instance, that 60% of weights, just setting that as zero. This is the weight can choose based on random, criteria, or based on math. There are a lot of heuristics to select which ways to shut down. However, usually people make a further retraining step after doing in order to fine tune the survival weights here. Okay. At task 2, what I do is basically maintain these weights frozen and learn the rate. Okay, so in Puppet, what we do is exploiting pruning in order to make the weights of 2 or more tasks to share the same mechanism or the same weights. Okay, so task 2, I basically print these weights and learn the remaining ones. After that, I apply another pruning stage on the orange weights. These orange weights are those learned during the second task and continues. At different time, I maintain all these masks. No. This is the mask 1 for class 1. This is the mask for class 2. And based on the mask, I will select which way activate to the make forward pass on each of them. Okay, so in pruning based tables, what I do here is avoiding introducing new parameters. Basically, I restrain in a sort of parameter efficient approach, in which we select only a subset of parameters. And at inference time, if my value comes from class 1, I use this mask to select weights and then start all these this one. In the second task, instead, I use the orange one. The mask with the orange one in order to filter the weights I should use, for example, from examples coming from task 2. Exceptions. Okay. So Bucket basically use the idea of binary masks to reduce the set of parameters that we should retain for each. Okay. Yes.
Why don't you use different networks? I see that over in the minute. Nice.
In order to save space and save number of parameters. To avoid the problem is that if I have many tasks, if I have one network for each task, for instance, let's consider a case where I have 100 of tasks, not storing 100 of bubbles.
Yeah, but I see that the model you're going to use have to have a lot of weights, so you can do that max for 100 tasks.
These maps are binaries, so are either 0 or 1, so they are very accurate.
Yeah, but not the mass system, but the weights of the wheel.
The way to do it, we just have one weight matrix in this case. Do this, then your weight matrix here, and you maintain one matrix for the weight, and you maintain in n masses, one for each task. And each mass is used to filter the weights you need from this weight.
But the size of that network shouldn't be super large compared to a smaller network for one task.
Okay. So you are basically saying that I could do the same using a smaller network.
Yeah, a smaller network for each task instead of a super large network.
With the yeah, it would be okay.
I think in practice, all these strategies are applied to the last feeling in the same way. You don't apply this to the future instructor, only apply it to one or two method at most. So you are interested in the future instructor, otherwise you should be need to start your training with your expectations and yeah, what's inside. Basically, they apply this. I think in the previous utilization, you talked about the progressive. I think in practice, on the implementation level, they only it makes sense to extend the last relevance of the because it can, it's not practical to do that in the middle of a let's say we use parts of the features which are important for the classification.
Yeah, it makes sense to apply these architecture to the end, to the final layers, because that layers we really want to use the entire concept for different classes. So it makes really sense. For your question, I will say that the problem is if we should not basically reduce the complexity of the model. We do not want to reduce the complexity of the model just by reducing the number of layers or the width, the channel width. Because in this way, we could lose the opportunity to, for instance, learning high-level transformations. And so the idea, I guess, is okay, let's remain on big architectures that give us the chance to learn more high-level features, more deep transformation from the output, but let's use pruning in order to still use very networks, but are reduced cost. This I think that it's usually learning what we want to do is avoiding problems, avoiding solving problems by reducing things. Usually the approach is the other. So a large things, but more regulars. So use, for instance, big networks, but with stronger system and stronger documentation. This is the common approach in there. In this case, the approach is okay. Let's stick to big models, but use pruning in order to prevent computational issues. Okay. Now let's talk about regularization. In regularization approaches, what we is not storing in parameters, not enlarging the networks. What we do is modifying the loss function. Okay? We modify this function in order to prevent the model from the One is EWC. We have seen that EWC is an approach that modifies the loss function in order to prevent weight drifting. Okay, so we penalize each deviation in a proportionally to the importance of the corresponding weight. The importance is calculated in the efficient information matrix and so on. There is another kind of approach that is based on knowledge distribution and knowledge transfer. The basic idea, the basic intuition is that when we learn on a new task, what we can do is to transfer the knowledge learned by the previous network on the current. So we learn model, but we learn a new model on the data from the current task, but also in conjunction, we transfer knowledge from the previous into the current one. Okay. This is done, for instance, through knowledge interpretation. So that's it. Okay. For instance, what we can do here, let's consider is the first the model learned in the previous task. So, and let's suppose that this is its weights are frozen. So we have learned these weights, and now we can keep them frozen. Let's suppose that we are learning a new model on task B. What we can do here is trying to regularize the output of this model in order to stay close to the output of the previous. Okay, so what we can do here is, for instance, given an example, we can make a forward pass here, compute the output, and then ask this model to yield the same output of this model. This is basically a teacher-student party where this is the teacher, so the network learned in the previous task is the teacher network, and the network learned in the current task is that student. What we do is basically encourage the current model to give the same output of the teacher model. Okay? Why this is because if all works, then we have transferred all these capabilities of the old model into the new model. Okay? We can do that using the idea of functional organization. So we can distinguish basically in general between weight organization, EWC, weight regularization, we penalize deviations in weights, and functional regularization. We penalize deviation in outputs. These are two distinct techniques. Penalizing weights, TWC, penalizing activation or output, that is all those models based on knowledge estimation or teacher student paradigms. Okay. Now we are going to see some example of function regularizations. Any question or observation? Have you got the concept, the vision behind function regularization? So yes, okay. I have to I read with my model, my current model is good also like this one. Okay. What an approach to guarantee that is basically while training this model, regularize each output to be close to the previous model. Okay. So we can do that. Functional regularization usually is performed at logic level. So we try to align the responses of the class-wide prediction of the two models, but also it can be applied in feature space. We can take the activation in intermediate applications from both models and try and teach the models and teach the current model to make its feature close to the ones in the student. So the take home message here is that we can apply the idea of maximum regularization in two parts. So at logic level, so by analyzing predictions, classified prediction, and also at feature level. So we can take the activation of two models and ask the student model to mimic that. One example, one approach is learning without forgetting. No? The idea of learning without forgetting is basically that of applying knowledge distillation. So knowledge distillation, what we do is aligning the logics, so the responses, the class-wide prediction of two models. So applying knowledge distillation between the teacher, your map, frozen parameters, and the student, so the parameters, learning the parameters. Okay. Still, what is the problem with that? No. Let's suppose we are on task 2. And I'll say that we want to transfer knowledge from task A to task B. But we are not on task B. How can we transfer knowledge between between model A and B?
Two examples of task A.
Yeah. In order to transfer knowledge, I should theoretically need example from the past task, from task A. No? Oh. Yeah, learning without forgetting overcomes this problem by using data from the current task. What does it mean? It means that basically, instead of relying on past data to make transfer, learning without forgetting uses data from the current task to make transfer. So it takes example from the current task, forward them to the past record, feed each example to the past method, and ask the model to output the same output. Right? Do you see any problem in doing that?
If I know specify head, shouldn't know the difference between samples of task A and task B.
Sorry, can you
Right? If you only pass samples of task B, for example, you add a new class, use all the labels that you're getting as from the new classes, and the new square head will never learn to classify to the previous classes.
Yes, so problem is that this works in one direction, but not in both. So we can transfer knowledge from classes of this task to classes of this task. So from the classification head of this task to the classification head of this one, but not the opposite direction. So basically, what we want to do here, what we do here is given an example from task B, we analyze the prediction for the classification head of task A and try to make the two head add A here and add A here to make the corresponding outputs align. So we align only class head for task A for the first case. The add for task B is not affected by this alignment. Okay. We could also make something in feature space. Okay, also. But still, just to provide you the idea, learning without forgetting employees knowledge distillation to make this transfer, but for making this transfer, and we should use example from past tasks, but since we do not have it, we surrogate this example by using example from the current. This is learning without forgetting in a few words. Okay. Basically, we should use example from past task, but we do not have it. So what we do is surrogate that example from the context. Okay. Yeah.
A is trained on images from the first task. I guess the response for both other would be based on an image. So you're actually teaching the head of the new model, so the head for task A, but on the new model, to be best for images. Like, okay, since I only have for task A, I would be give like prediction for images on the task A. It's like forcing, it's teaching, but forcing the that head to be better. So you are more specific.
Yeah. In this case, okay. Let's try to analyze which information is going to capture class if we had for task A given an example from task B. In this case, that ad probably will have something that is still meaningful because basically, for instance, let's suppose this task has learned cat versus dog. If in this task I'm learning foxes, foxes are not neither cat or dog, but in terms of predictions, we could still learn something from the output of a day. For instance, that a fox is more than a dog than a cat, for instance. And we want to transfer this knowledge. So there is something useful here. Okay, we will transfer to task B. Okay, this is the equation. So there are so-called secondary informations. So the concept of secondary information, distillation is that if we analyze the distribution of the output, distribution of logics, there is something really, really informative about the input. And we want to transfer that knowledge to another level because it encapsulates some high-level knowledge about the examples. For instance, some strange relation between classes, given
And
the example.
especially if you're not stretched, so of course, that's it.
Yeah. Okay, I will probably stop here, make a coffee break.
Yeah, sure, perfect. We come back at maybe a quarter to 12. We can come back. No, 25 minutes. Quarter to 12. We continue. Yes. Okay. Thank you.
Before